Hello everyone, welcome to today's MOOCs class. I am Rosalind Mishra, Assistant Professor, ITS College of Pharmacy. Today, in today's class, we shall be learning in detail about aliphatic carboxylic acids. This is a continuation class wherein we will be dealing in detail about properties of carboxylic acids. In the last class, we had left at discussing about boiling point, melting point, acidity of carboxylic acids, whereas in today's class we shall continue the same topic on the same line with a lot more details. Alright. So, before delving into the class, let us first understand that what would be the content of this unit, that is aliphatic carboxylic acids and aliphatic amines. Okay. Now, the acidity in under this unit we shall be dealing with aliphatic carboxylic acids. Okay. So, under aliphatic carboxylic acids, following are the topics which we shall be delving into: acidity of carboxylic acids, effect of substituents on acidity of carboxylic acids, inductive effects, qualitative tests for carboxylic acids, amides and esters. We shall be looking into structures and uses of acetic acid, lactic acid, tartaric acids, citric acids, succinic acids, oxalic acids, salicylic acids, benzoic acids, benzyl benzoate, dimethyl phthalate, methyl salicylates and acetyl salicylic acids. We shall also be learning about aliphatic amines, mainly basicity of aliphatic amines, effect of substituents on the basicity of aliphatic amines, qualitative tests, structures and uses of a number of amine derivatives such as ethanolamine, ethylene, diamine and amphetamines. Okay. So, now let us move into our topic. Now, let us learn about pKa of acids. The pKa is the measure of strength of acids. The pKa of some typical carboxylic acids I have listed in the table, which we will be looking into in the continuation. When we compare the pKa values with those of comparable alcohols such as ethanol, 2-methyl, 2-propanol, it can be very well clarified that carboxylic acids are stronger acids by over 10 powers of 10. Furthermore, electronegative substituents near the carboxylic group also increases the stability. Okay. Hence, acidity also increases the acidity. So, presence of electronegative substituents or an electron withdrawing group increases acidity. Here I have listed down the pKa of some typical carboxylic acids. What is this pKa value? It is the measure of strength of an acid. Suppose if we take for example formic acid HCOOH, the pKa value of this compound is 3.75. HCOOH, the pKa value is 3.75. Similarly, the pKa value of carboxylic acid or acetic acid is 4.74. pKa value of another acid 2.65, or presence of this halogen fluoroacetic acid increases the acidity, hence decreases the pKa value, which is 2.65. Similarly, chloroacetic acid has a pKa of 2.85. Bromoacetic acid has a pKa of 2.90. Iodoacetic acid has a pKa of 3.10. Trichloroacetic acid has a very small pKa which is 0.77. So, in the previous slide, likewise we had discussed presence of electron withdrawing groups or presence of electronegative atom on the carboxylic acid. Okay, presence of electronegative atom on the carboxylic group increases acidity. This can be proven by looking into the pKa values of various derivatives of acetic acid, like for example fluoroacetic acid, chloroacetic acid, bromoacetic acid, iodoacetic acid and trichloroacetic acid. More or stronger the electronegativity of the attached atom or more the electron withdrawing effect of the attached atom, lesser is the pKa value, hence greater is the acidity. Okay. Lesser is the pKa value, hence greater is the acidity. Similarly, here we have a few propanoic acids and butanoic acids and their derivatives wherein the pKa value can be observed. Now, moving on further. The pKa of carboxylic acid is typically -5. They are significantly more acidic than water or alcohols. Now, let us discuss about another theory known as Bronsted acidity. Carboxylic acids transfer a proton to water to give hydronium ion and carboxylate anion. Okay. So, what happens when carboxylic acid is dissolved in water? When carboxylic acid RCOOH is dissolved in water, then two major molecules are formed. Okay. A carboxylate anion RCOO minus and a hydronium ion, via H3O plus. So, the Ka value can be written as RCOO minus, the RHS side RCOO minus H3O plus whole together divided by RCOOH. Water being the solvent here is taken as negligible. Okay. So, typically this has a value of 10 to the power minus 5. So, the pKa which is minus log Ka is approximately 5 for a carboxylic acid. So, you can see increasing acidity trend with an alkane, alcohol, phenol, acetic acid or carboxylic acid and hydrochloric acid. Okay. So, this is an increasing trend of acidity starting from an alkane to an alcohol to a phenol followed by an acid followed by hydrochloric acid, which is considered as a strong acid. Now, let us again learn a few points about solubility and appearance of carboxylic acids. Many carboxylic acids are colorless liquids. They have a disagreeable odor. The carboxylic acid with 5 to 10 carbon atoms have a goaty odor. Okay. Next, these acids are also produced, these carboxylic acids are also produced by the action of skin bacteria on human sebum or skin oils, which accounts for the odor of poorly ventilated rooms. The acids with more than 10 carbon atoms are wax-like solids and their odor diminishes or decreases with increasing molar mass and resultant decreasing volatility. Carboxylic acid exhibit strong hydrogen bonding between molecules. They therefore have high boiling points compared to other substances. the carboxyl group readily engages in hydrogen bonding with water molecules. The acids with 1 to 4 carbon atoms are completely miscible with water. Solubility decreases as the carbon chain length increases. It is because the dipole forces becomes less important and the dispersion forces become more predominant. Okay. So, these were the few characteristics of carboxylic acid in terms of solubility and appearance. Next, solubility of the bigger acids decreases very rapidly. Okay. As the carboxylic acid chain length increases, the solubility decreases. It is because longer hydrocarbon tails of the molecule gets between the water molecule and breaks down the hydrogen bonding. Okay. As the carbon chain length increases, solubility in water decreases. It is because the ability to form the hydrogen bond also decreases with this increase in the chain length. Okay. These carbon chain length or the length of this carbon chain of the alkyl group breaks the hydrogen bonding. It comes in between the hydrogen bonds. In this case, these broken hydrogen bonds are only replaced by much weaker van der Waals forces or van der Waals dispersion forces. So, to put it in simpler words, as the chain length of alkyl group increases, hydrogen bonding diminishes, the force of hydrogen bonding decreases and the dispersion force or the van der Waals forces increase. Van der Waals force are much weaker. Next, hexanoic acid is barely soluble in water, about 1 gram in 100 grams of water. It is because of 6 carbon hexane chain or 6 carbon alkyl chain. Next, palmitic acid with its large non-polar hydrocarbon component is again insoluble in water. The carboxylic acids generally are soluble in such organic solvents like ethanol, toluene and diethyl ether. Here if we see, these are the structures of water molecules and carboxylic acids, where oxygen atom of carbonyl group forms hydrogen bond with water molecule. Okay, with water molecule. Here oxygen atom of carbonyl group forms hydrogen bond with water molecules. Okay. Similarly, here hydrogen atom forms hydrogen bonding with various water molecules. These are the different hydrogen bonds wherein bonding takes place between oxygen atom of the carbonyl group and the hydrogen atom of water molecule. Okay. So, next moving on further, here we have a table of condensed structural formula. Okay. Their melting points, boiling points and solubility in water. If we take for example formic acid having a molecular formula of HCOOH has a melting point of 8 degrees Celsius, has a boiling point of 100 degrees Celsius and is freely miscible in water. Similarly, moving on to the next compound, which is acetic acid. Acetic acid on the other hand has a melting point of 17 degrees Celsius. It has a boiling point, a higher boiling point of 118 degrees Celsius, that is the boiling point is greater than water. Okay. So, 118 degrees Celsius. This is also found to be miscible in water. Moving on to the next compound, propanoic acid has a melting point of minus 22 degrees Celsius. It has a boiling point of 141 degrees Celsius and is miscible in water. Similarly, next compound, butyric acid, has a melting point of minus 5 degrees Celsius, boiling point of 163 degrees Celsius, and again it is miscible in water. Next, moving on to valeric acid. Valeric acid has a lower melting point of minus 35 degrees Celsius. It has a boiling point of 187 degrees Celsius and only 5 part is miscible in water. Next, caproic acid has a melting point of minus 3 degrees Celsius. It has a boiling point of 205 degrees Celsius and again it is partly 1.1 gram per 100 grams miscible in water. Similarly, benzoic acid has a melting point of 122 degrees Celsius. It has a boiling point of 249 degrees Celsius and again it is partly miscible, that is 0.29 grams in 100 grams of water miscibility. Okay. Next, when we talk about boiling points of carboxylic acids, the boiling point of alcohols are higher than those of alkanes of similar size, because alcohols can form hydrogen bond with each other as well as van der Waals dispersion forces and can also form dipole-dipole interactions. Okay. Similarly, the boiling points of the carboxylic acids are still caused by hydrogen bonding, but operating in a different way. How? In a pure carboxylic acid, hydrogen bonding can occur between two molecules of acids. Okay. In a pure carboxylic acid, hydrogen bonding happens between two acid molecules, between two molecules of acids to produce a dimer, to form a dimer. This immediately doubles the size of the molecule. So, increases the van der Waals dispersion forces between one of these dimers and its neighbors, resulting in a higher boiling point. Okay. So, here with the help of this diagram, hydrogen bond between fairly positive hydrogen atom and a lone pair on the fairly negative oxygen atom, fairly negative hydrogen atom and fairly negative oxygen atom, a hydrogen bonding can be seen. Alright. So, this helps in increasing the boiling point of carboxylic acids. Talking about melting point of carboxylic acids, in the first 10 members of the homologous series, the alteration effect is observed. The effect implies that the melting point of an acid with even number of carbon atoms is higher than that with odd number of carbon atoms. Above, whereas no effect is observed in homologous series with more than 10 carbon atoms. The alternation effect is due to the fact that in the carboxylic acids with even number of carbon atoms, the terminal methyl group and the carboxylic group are on the opposite side of the zigzag carbon chain. Hence, they fit better in the crystal lattice and it results in a stronger intermolecular forces. Hence, owing to the increased melting point of carboxylic acids, or hence owing to the characteristic melting point of carboxylic acids. On the other hand, in acids with odd number of carbon atoms, the carboxyl and the terminal methyl groups are on the same side of the carbon chain. Okay. Hence, the molecule fit poorly in the crystal lattice. Because of their being relatively unsymmetrical, so the intermolecular forces are weak and the melting points are relatively lower. Moving on to the qualitative tests for carboxylic acids. A few drops or a few crystals of the unknown sample are dissolved in 1 ml of methanol. Okay. The first test, few drops or a few crystals of unknown sample we take and we dissolve in 1 ml of methanol. To this we slowly add 1 ml of a saturated solution of sodium bicarbonate. Okay. So, if our unknown sample is an acid, upon reaction with sodium bicarbonate NaHCO3, it produces or it gets converted into a sodium carboxylate anion along with production of carbon dioxide, along with production of CO2 or carbon dioxide. This carbon dioxide leads to production of effervescence. Okay. Hence, we can confirm that our sample is an acid. Evolution of carbon dioxide gas is a positive test for the presence of carboxylic acids. Okay. So, this test is also shown by a few phenolic compounds. Okay. So, this is one of the identification tests for carboxylic acid, production or removal or evolution of carbon dioxide gas. Another test for identifying carboxylic acid is litmus test. Okay. A drop of liquid compound or a drop of solution of the compound with the help of a glass rod on a moist blue litmus paper is put. Okay. If the blue color of the litmus paper changes to red, then the presence of either a carboxyl group or a phenolic group is indicated. Okay. So, if a blue litmus paper turns red, then this indicates the presence of carboxylic acid. So, we take the unknown compound, we put it or we place it on a blue litmus paper. If we observe a change in color to red, this signifies the presence of carboxylic acid. Another test, sodium hydrogen carbonate test. Okay. So, the third test for identifying a carboxylic acid is sodium hydrogen carbonate test. 2 ml of saturated aqueous solution of sodium hydrogen carbonate is taken in a clean test tube. To this, few drops of liquid compound or a few crystals of solid compound, whatever our unknown compound, is added. The evolution of a brisk effervescence of carbon dioxide indicates the presence of carboxyl group. Okay. So, if effervescence is produced, this indicates the presence of carbon dioxide, the presence of carboxylic acids. Next, we will move on to test for amides. So, for carboxylic acid, we have seen 3 tests. Moving on to test for amides. Reaction of sodium hydroxide. Okay, test involving reaction of sodium hydroxide. Amides are decomposed by sodium hydroxide to evolve ammonia. This gas can be tested by a moist red litmus paper, which is then turned to blue. Amides, upon reaction with sodium hydroxide or a base, gets converted to form sodium salt of carboxylic acid, RCOO minus Na plus, sodium salt of carboxylic acid with the evolution of ammonia. Okay. So, this evoluted ammonia can be tested or can be identified using a red litmus paper. If the red litmus turns blue, this signifies the presence of a base which is ammonia, or evolution of ammonia gets confirmed. Next, another test which we perform for testing of amides is alkaline hydrolysis of aromatic amides to aromatic acids. The soluble sodium salt of aromatic acids formed from aromatic amides upon hydrolysis is regenerated as white precipitate in acidic medium. Okay. So, when aromatic amides are made to react with sodium hydroxide, then ammonia is evoluted via the formation of aromatic acids. Next, biuret reaction for aliphatic amides. When aliphatic diamide is heated at a temperature above its melting point, ammonia is evolved and crystalline biuret is formed. This biuret in alkaline medium gives a violet color with a drop of copper sulphate solution. The next test is hydroxamic acid test for primary amides. Hydrogen peroxide reacts with aromatic primary amide to form hydroxamic acid, which then reacts with ferric chloride to form ferric hydroxamate complex, which has a violet color. So, with this we finish up our today's topic, wherein we have learnt or we have continued our previous class discussing about properties of carboxylic acids and various identification tests for acids and amides. Okay. So, with this we end our today's class. Thank you all.